Welcome. This is our second week. That means thank you for joining me. And this, as you probably noticed, based on the emails or announcement, I will actually run 2 live sessions per week because I just want to accommodate as many students as I can. It's not possible to accommodate everyone, but you can. I just want almost everyone to have a live session experience. That means based on your preferences, I will run the session at 1 p.m. Tuesdays and Wednesdays. Both of the sessions are going to be different. They will be different because I will split the weekly material by 2, and I will cover half of the stuff, the weekly stuff, Tuesday, and the other half on Wednesdays. I'm just reading the questions on the chat box. Oh, you can't, can you hear me? You can't hear, Colin, can you hear me? Okay, Sarah can hear, okay, you can hear me, right? Because I see that Colin is saying you, or maybe that's something, okay. Okay, good. Okay, thank you. I don't want to talk. And okay, one thing that maybe you can do, and I think, Colin, you can switch off your video. And of course, mute your microphone. Then we will not, the voices will not collide. Let me double check. Okay, Colin. I will stop the video for you. It's just a little bit better too. I will switch off too because it's better to focus on the board, on the whiteboard. Okay, that's when you don't. Cody, you saying that you only have option to hear me? You can't see the screen? Okay, I think if you will log in through your computer or the smartphone, I think you can also see the stuff because, of course, this is the math lesson. That means it's worth to also see, not only hear. Okay, I don't want to take time. All of the admin, all of the technical problems, I think we can figure out. But one more time, we will have a session today, Tuesdays and Wednesdays at 1 p.m. And as I said, it's worth to attend. If you can't attend, of course, you can watch the session, and this is still considered as a good participation. It's just worth to experience, to be live, because it's like actually being in the classroom. You have the possibility to ask me a question, or you can answer my questions. It's a little bit more interactive when you are actually live. Okay, that means let's start. I will switch off my camera, but I'm here. That means what we have this week, we will finish chapter 1 with section 1.8, continuity, and then tomorrow I will start chapter 2 and I will cover section 2.1 and 2.2. That means that's the sections that's the material for this week. And let's see, continuity. We did learn the basic concept of calculus, which is the limits. We did practice in section 1.6 how to calculate the limit. Now we will use it for defining and proving the continuity of the function. Okay? But first of all, we have to understand what continuity means. And if we will think intuitively, it's something like something that is continuous, right? Like no breaks, no jumps, no asymptotes, no removed points, like something nice and smooth. And if I would like to draw a function, a curve that is continuous, like I will not leave the pen from the paper. Yeah, like let's say I can draw something. Can I draw something? Without, as soon as I leave the pen and come back, I may do some interruption, some discontinuity. That means if something can be drawn without lifting the pen, we consider this as a continuous curve. Right? Something. And we will talk more precisely about the continuity at one point. And then we will expand this for the entire interval, entire domain. And we will use, of course, the limit concept. Let's see. I just draw a function for you, like the blue curve. It's definitely continuous function. And as I just said, I can take a pen and draw without lifting the pen. But more mathematically, what I would like to focus on is to focus on that point, A, f of A. We can see this dot. And what's happened? Of course, the point A, right? Point A is in the domain of the function. Because if the point A will be not in the domain, then automatically we do have some problem, some discontinuity. And then the point A is in the domain, and we can definitely see that the value at A exists. Okay? We do have definitely the value, the solid dot. And another thing, it's interesting, the limit, okay, of the function at A also exists. Let me actually name this maybe L. The value is L and the limit is L. Okay? That means this point is L. That means actually this will be a definition. Looking at the function and testing the continuity at one point, we have to check the value, what is the value, and what is the limit at this point. If the value match the limit, then we can say that function is continuous function at the point A. Okay? I mean, of course, this is more theoretical part, but we know that almost like all of the, some applications, almost all of the physical phenomena are usually continuous. Yeah? They are on constantly without any breaks. We may have some situation with the power, with the electric currents, that we may have we know we can have the stop, like when we have the supply in electricity, but we may also have a break. Yeah, everybody experience this. But most of the physical things are continuous. That means it's worth to know how to check if the given model, given expression, given function is continuous. Okay, let me now look at this. This is the same that I just said. Function f, it's continuous at the number A. If A is in the domain, the value of the function at A is defined. The limit also exists, also is defined, and the limit and the value is the same. Of course, I'm saying the same, but we do remember from section 1.5. I hope you still understand the concept of the limit. We know that they are not exactly, in terms of the definition, in terms of the meaning, they are not exactly the same, but they will have the same value, like the same output, and we call the same. That means some of the textbooks, some of the instructors, they will just tell you this. This is the definition of the continuity. If the value exists and is the same like the limit, then function is continuous function. Okay, that means now let's just use it this. That means this is the most important thing. Oh, I wanted to draw a star. Limit the same like the value. And let's see what we have to do. Okay, before we start practicing, we also have some definition, some continuity, or like one-sided continuity. We may have a function, the value of the function being exactly the same like one-sided limit. And we can actually call that the function is continuous from that side, from the right or from the left. And for example, I can draw an example, x, y, and maybe a function. And at A, this is m, this is k. As we can see, can you tell me what is value? What is the value at A of the function f of x? That's A. Yeah, that's what is the value? Can you tell me? It's k. Yes, thank you. It's k. And can you tell me what is the limit of the function as x goes to a from the right-hand side? The limit from the right-hand side, of course, is k, because we can see the solid dot, the value is k, but also the function is approaching from the right-hand side, is approaching that dot, that level. Yeah. Thank you for your answers. That means the right-hand side limit and the value is the same. We can say that function is continuous from the right-hand side, and respectively will be on the left-hand side. And we can see it's weird because we do have discontinuity, but this is a special type of continuity, the one-sided. Okay, that we also remember about this. Okay, example number 1. We do have a figure in the graph, and we have to figure out at which numbers the x values is f discontinuous and why. Yeah? Because discontinuity, it's kind of like a problem, and we always have to define a problem. Yeah? Because the mathematicians, they always have problems, but they trying to, that's actually the point of being mathematician. Yeah? Without the problems, they will they love to solve the problems. But having a problem, we have to explain, we have to justify. Okay, let's look at this curve. Of course, we're assuming that it goes to the infinity, okay? And yeah, we do have some problems, right? And we will name the problems, okay? We will label them. That means, first of all, can you tell me what are the potential numbers that we seeing a problem at? Do you think, oh yes, oh, somebody is, yeah, Jake, it's fast. 1, 3, 5. Oh yeah, you said 6. For some reason I put 7, but you actually right. This is supposed to be 6. Shall I change it? I will change it, okay. I think I was using in my other slide 7, but yes, okay. That we can definitely see that's the problems. Before we start analyzing, can you tell me what's the domain of the function? Do we have all of the numbers in the domain? Or we have some numbers that are not in the domain? 1, I am okay with this one. That means 1 is not in the domain. And Maria said 5 and 6. I think I am okay with 6, but what about 5? Can you see that we do have a corresponding? Yes, 5 is actually because we do have a value. As soon as we draw a vertical line and the vertical line is intersecting at least one point, I think has to be 1 point because it's function, then the point is in the domain, okay? Yeah, yes, it's the dot above, right? Yeah, that means 1 and 6 is not in the domain. That's, of course, that's definitely a problem, but we still have more points, okay? That we do have, let me actually write down, we will investigate that point, we will investigate this one. We have problem here, and we have problem here. Of course, this number and this one is not in the domain. That's automatically we looking at, and from the graph we see 3 and 5. Okay, let's investigate what's the problem. This is just the same graph, a little bit smaller, and we looking at 1. With respect to the discontinuity, I have to check the limit. That means now I will go even deeper in the details, limit from the left, limit from the right, and the value. And the ideal situation is if all of the numbers are the same, but we know that they are not the same. Okay, that means now get ready to your keyboard and type the answer for me. Looking at the function, hopefully we can see the function. What is the limit on this function at 1 from the left-hand side? 1 from the left, it's 1. What is the limit at 1 from the right-hand side? 1, thank you. Wow, the chat box is like rolling, really good. What is the value at 1? Yes, thank you. I will use and this is like a set notation, empty set, but DNE, yes, DNE is perfect. Okay, great. That means we can definitely see that all of the three values are not the same. We do have a problem. You actually knew it. And let's see. That means this is my kind of conclusion. The limit exists, limit is 1, but the value doesn't exist. And of course, it's different. The limit, Sarah is saying that the limit exists, but no value. Yes, because we do have an open. Can you see the open circle? The value, like exactly if I will draw a line, nothing is on the line. But, I don't wanna, but really close, as we're getting really close to 1, function is approaching that level, which is also 1. Yeah, that's me, a limit exists. Okay. I'm sorry, I'm just some noise on my screen. Okay, that's me now, because what I have to do, we have to name the type of the discontinuity. And I don't want to really ask, but maybe I could. Do you remember what type of discontinuity is this? We do have a calculation and we have the graph. Okay, Eric, yes, we can call point, which means only one point is removed. And our textbook is using this, removable discontinuity. Yes, but if you will say point, it will be also correct. Okay? But please remember that probably on the test, on the quizzes, on the exams, I will use the textbook terminology. But yes, that's it. It means that removable, only one point is removed. And how we can see? From the graph, it's extremely easy. But from the limit, we can see the limit exists and value is different. Could be none, or could be, the dot could be somewhere else, like somewhere here, for example. This will be the same thing. Okay? But we can see different. The limit exists, but different than the value. This means the limit exists means that function does the same thing. Only one point, it's different. Okay, that's when we have a removable discontinuity. Let's look at x equals to 3. Okay, limit from the left, limit from the right, and the value. Okay, get ready. Yes, fingers on the keyboard. Looking at the graph, what is the limit at 3 from the left-hand side? Yes, thank you. Wow, okay. Eric, Madeline, Kendrick, Jake, Alan, Eric. Yes. Okay, -1. I typed correctly. Limit at 3 from the right-hand side. Yeah, I think it's 4. Yes, great. Oh, we definitely have a problem. And now the last one, what is the value at 3? It's also -1. We can see the solid dot. Excellent. Let me write this. Again, my conclusion. Oh, no. I didn't want to show you the name. Oh, Kasia. Limit, since the one-sided limits are different, then the limit is undefined. Right? We do have left and the right-hand side, but overall the limit is undefined. And the value exists, but it's different. I mean, how could be the same if this is not even exist as a one finite number? Okay, but looking at the graph, and even this will tell us if we not have the graph, if we have two different left and the right-hand side limits. That means what type of discontinuity is this? Did you? Yes, thank you. Oh, wow, you fast with your writing. Yeah, it's the jump discontinuity. But please remember, jump means this. Left and the right-hand side limit is different. And theoretically, we don't even care, I can say maybe this way, for the value. Value could be anything. Could be -1, could be 4, or could be even somewhere else, or could be undefined open circles. If the limits are different, it's jump discontinuity. Okay, good. Okay, another one, 5. Limit from the left, limit from the right, and the value. Okay, ready. What's the limit at 5 from the left? It is 1, yes, yeah. Limit at 5 from the right. It's also 1. And what is the value? Value is 5. Yes, I think, yeah, you're looking good at my graph because it's a little bit tiny, but you're good. Okay, 1, 1, which means the limit exists, value exists, but it's different. And what do you think? What type of discontinuity is this one? Yeah, the limit, it's fine, exists, but the value is somewhere else. Yeah, look at 1. It's the same thing. Yeah, because function does the same thing. If I will put back that point, I can simply draw the function by 1, like go, right? I can simply draw it's kind of like parabola. But since 1 point is gone somewhere else, it's gone completely at 1, but it's put it somewhere else at 5, that's still fine. Yeah? But this means that it's removable. And always when the limit exists and value doesn't match, or it's completely undefined, that's how we can recognize removable discontinuity. Okay, good. And then 7, I know I said, because for some, I don't know why I put 7. And this is my handwriting. Okay, let me correct this. It's 6, because you definitely... Okay, that means now, what is the limit of the function at 6 from the left-hand side? Do you think? Yes, it's positive infinity. Thank you. On the right-hand side? It's also positive infinity. And what about the value, the exact value at 6? Thank you very much. It's undefined. That's we do have this limit. It's undefined, but it's infinity, and the value is undefined. Do you think you know the name, or you can maybe guess the name of the discontinuity? Yeah, we can say disjoint. Oh, yeah, we can say infinite discontinuity. Yeah, or asymptote. It's still fine. Of course, I will understand the logic. But we will follow James Stewart, we will follow the textbook, and the terminology is in infinite discontinuity. And how can you recognize? As soon as one of the limits is infinity, you can always say infinite. If the infinity is involved in some way, you can always say infinite discontinuity. Yeah, that's the good way. Okay, that means you know all of the types: removable, jump, and the infinite. Now, example number 2. We do not have graph, we have just the formula. Where are the following function discontinuous? That's what we have. We have 2 different pieces. We have a rational function, x squared minus x minus 2 over x minus 2. And this function is defined wherever x is not equal to 2. That means everywhere, but not at 2. At 2, we do have the value 1. Right? That means what this means, of course, I don't know how function looks like. Let me draw something just for now. That means at 2, we definitely have a problem. Right? And if the question is asking where are the following function discontinuous, we probably guessing that we will have problem at 2. Right? Because at 2, we do have the value 1, but I don't know what is the limit. That means I really have to check the limit on the left and on the right-hand side, left and the right-hand side. Because maybe, I don't know, maybe function actually meet. Yes, from the left-hand side and the right-hand side, maybe function will have a limit 1. That means I will still have actually continuous function. But what we have to do? We have to check the limits. Let me remove this because the graph will look a little bit different, but that was the idea. Did I type it, but I can write for you. Limit as x goes to 2 from the left-hand side. And I can, and limit as x goes to 2 from the right-hand side. Okay, we have to compute these 2 limits. And see, maybe the limit is 1, but I don't know. But first of all, if I will substitute 2, we remember the direct substitution, section 1.6. If I do the direct substitution, I have 2 squared, 4, minus 2, minus 2. Okay, 0. And 2 minus 2, 0. That means I do have 0 over 0. But we remember from week 1, the answer is most likely not 0. This is telling me that I have a common factor. at 2, both of the functions from the numerator and denominator has a common factor. And I have to find this common factor and cancel out. This will be the process to eliminate that 0. Okay, I have nothing to do here, but do you think you can help me factoring the quadratic, yes, expression? We have x and x, 2, my writing, yes, yeah. Oh, x minus 2x plus 2, let's see. The factors of 2 is 2 and 1, and I need -2 and +1. I think Maria was right. You can, yeah, okay, Eric. Because sometimes, of course, we can always double check. This will give me, okay, perfect. And now we can see that's my common 0. That's my common factor going. That means I did manage to simplify a function to just x plus 1. Now I have no problem. I can simply do the direct substitution. 2 plus 1. The limit is actually 3. That means the limit on it's different than the value. We definitely have discontinuity. And for this one, I can see that I can simplify function the same way. And doesn't really matter if it's from the left or right. I have no problem. I can substitute. Okay, that means limit exists. We can see, but the value is different. I can show you the graph, but before that, do you think you can tell me the type of discontinuity? It's, yeah, the point, how we call the point. I know, Eric, it's the removable discontinuity. Really good, thank you. Because we can see function will do, I know how function looks like, but I will tell you in a minute. 2 and 1. Actually, oh no, okay. I just want to give you the idea, but I can show you the graph, actually the real graph, because we can see what's happened. Our function, rational function, which looks a little bit complicated, we managed to simplify to that form. That means this function is simply just x plus 1. It's a linear function. It's just y equals to x plus 1. And y equals to x plus 1 is just the line. With the y-intercept 1, x-intercept -1 is just the line. But we still have to remember, this line came from this. And this expression were not defined at 2. That means at 2, we do have removed point. And we know what is this. Can you tell me this question mark? What is this question mark? It's actually 3. That's what we calculated. I can maybe draw it nicely, because that's the value is actually at 1. But this question mark is my limit, how function behaves. The line is at the level 3. It's like we can see from the left and from the right hand side, it's approaching 3. Okay? That means that's actually the line with the dot. And I think I type the solution for you, and I even have the graph. I knew it that I have somewhere, but I always want to solve with you the problems, okay? That's we can see that's the way to look at this, okay? Now what we will do one more exercise, I can show you, and then we have one more theorem, and we will be done. But thank you, you actually excellent students. You answering my questions, that's what I mean, that's what I like. Okay, shall we do this? Okay, let's do a little bit faster. It's a long question, okay, but I just want you to get the idea. That means this question is almost the same that we did with the graph, but now without the graph, I'm giving you a formula for the function, which is a little bit longer than the previous one. And based on that, I want you to be able to recognize a few things. Okay, that's what we have. The same thing. Find all points of discontinuity for this function and possibly sketch the graph. We have 3 different formulas, 3 different pieces, piecewise defined function. And I can draw something. Oh, this is supposed to be a nice number line. we can see at 0 and at 3, we definitely changing formulas, okay? Because I would like you to see this a little bit better. At 0 and at 3. That means, what do you think? 0 and 3. Are we going to investigate 0 and 3? Yes, definitely. That means the first points, because you have to find all of the points of discontinuity. Remember, always take these points. 0, I mean the points that we change in formula. 0 and 3. This is one formula, I don't know, it's a function, and this is another function. That means maybe they actually meet at one point. That means maybe the limit is the same, maybe the value is the same, but that's what I have to investigate. And now, let's see. X, I mean, the first formula is defined for x less than 0. That means less than 0 means on the left-hand side. We do have this formula, okay? Now, between 0 and 3, what do you think? What formula is defined at 0 from the right and the 3 from the left? Which formula we will look if we have to, is the second one, thank you. Can we simplify the second one? Maybe I can write here x, and can you see that I can simplify to this? Yeah, that means the common factor x. We still have to remember x is giving me 0 in the denominator, but function is not defined at 0. That means I'm actually fine. Okay, I will put the simplest form. And now, if we will investigate a limit at 3 from the right-hand side, which formula we will use? The third one, thank you, really good. And actually, the third one, do you think we can simplify the third formula? Yes, x minus 4, x plus 4. And I will switch the sign, and we can see the common factor with negative in front. Yeah, that means the third formula changed a little bit, okay, and looks like that. Okay, that means now if we have to look at the limit from the 0 left, we're using this one, 0 right, this one, and so on. Okay, but we still have a few points that we still have to investigate. Looking at the first formula, what do you think? What point is suspicious? What point we have to investigate? -2, because this function is not defined at -2. That we have this will be no value. Okay, that means -2 we have to investigate what is happening from the left and from the right hand side. But from the left and from the right, we will use this formula, no problem. Okay, what about the middle function? What value? 2, thank you. 2 is not in the domain. And what about the last one? Actually, 4, really good. Even if it doesn't look like, can you remember, this form came from this one. And we still had denominator, and this original function was not defined at 4. Okay, that's we have all of these points. -2, 2, and 4 are not in the domain, which we have to investigate what's going on. 0 and 3 are the numbers that we're dividing at different formulas. Okay. And now what I said, this is the most important part for me. I want you to understand, like to get ready, to set up everything, looking at the formula. Okay? That's what I wanted you to know. Because now what I will do, you probably know, I will take each number and compute the limit from the left, from the right, and the value. 0 from the left, from the right, and the value. Okay? Maybe we can get the values. Will be easier. If the number is not in the domain, we have no value, right? That's nice and easy. No value. But who can tell me the value at 0? Value at 0 is which formula we can use. Yes, Maria said 1, Cody. We have to use the first formula because we can see the equal sign. At 0 is the first formula. If you substitute 0, 2 over 2, of course, is 1. Thank you. Now, what is the value at 3? Oh, Which formula we can use? The last one, yes, thank you, the third one, because we do have the equal sign. And the third one was simplified to this one. Can you substitute 3? Oh, no. -7. 3 plus 4 is 7, and negative in front. Yeah, probably you did subtract. Or maybe you use this formula and you make some mistake. I mean, yeah, this will be -7. Okay, that way at least we have the values. Yeah, okay. We can use the simplest form. And now we have to do the limits, but I will do a little bit faster. I mean, you can probably help me, but let's do a little bit faster since you know what we're doing. Okay, that's me -2. The same idea like I did for the graph. Limit from the left, limit from the right, and the value. We know the value doesn't exist. But based on the formula, do you think you can tell me what is the limit? If we put -2, -2 plus 2 is giving me 0. That means 2 over small number is a big number. We remember that. But we have to investigate if it's, yes, right, positive or negative. -2 from the left, it's like -2.1. That means it's a little bit more than this. This will be negative. We will have negative infinity. Thank you, Maria. That's correct. That means this is negative, and respectively on the right-hand side, it's positive. We know this. And really quickly, what type of discontinuity we have? Do you remember? It's the infinite. Thank you. Oh, no, not removable. As soon as we see infinity, it's always infinite. Yeah? Always. Yeah. That means what I'm assuming that my graph at -2 will give me an asymptote. On the left-hand side, function will go down. On the right-hand side, function will go up. Right? Just, yeah, and no value, of course. Okay, let's keep moving. 0. 0 from the left, 0 from the right, and the value. Oh, that's nice and easy limit. Can you tell me 0 from the left? Yeah. Fingers on the keyboard? No. We can just substitute 0. We can, yes, well, thank you. We can just simply do, oh, this is supposed to be, actually, am I right with the functions? I didn't ask you this. Do you agree that this function is on the left and this one is on the right? Do you remember from the graph, from the number line that I draw? Yeah, because that's important. Okay, that means limit from the left, it's 1. Limit from the right, can you type the limit from the right? Yes, thank you. Let me, one thing. I'm just looking. Okay, and yeah, I think I have it. -half. Thank you. And do you remember value? What was the value at 0? We can use the top formula. The value was 1. Okay. Okay. Yeah. Okay. That means now we do have this situation. And can you tell me what type of discontinuity? It's just one. Oh, no. If we have 2 different limits, the function will definitely jump. Yeah. Okay, that means we can, because we have to get the graph. We did have an asymptote, this, and now at 0 from the left, we will have 1, and from the right-hand side, we will have negative. And 1 will have a solid dot because the value is also 1. I don't know if the function is going down or up because I have to check the next value, 2. 2 from the left, 2 from the right, and the value. Okay. Okay. The hands on the keyboard. What's the limit? And we know actually we know why I'm using this. Yeah. You can get back to the number line and see, because 2 is inside that interval. That means the simplest form of this function looks like that. Okay, can you tell me the first limit from the left-hand side? Negative infinity, good. And from the right-hand side? Of course, positive infinity. And value was not defined because it's the 0 of the denominator. What type discontinuity? Of course, the infinite, because we do have, that means we do have another, that's negative 2. Do you remember? I think I am right. At 2, we have negative infinity and positive infinity. Okay, we're getting the graph. Excellent. And we do have one more. Oh no, 2 more, 3. Limit from the left, limit from the right. We can see because 3 is on the, it's dividing the number line. That means this is left-hand side, this is right-hand side. You can check the number line at the beginning. And value. Okay, can you tell me the limit from the left? Thank you, really good, everyone. Yes, and what about limit from the right-hand side at 3? Yes, thank you, wow, okay, -7. And what about the value? We did the value, but hopefully you remember, you can see this in -7. Yeah, -7. Okay, that means limit is undefined because it's 2 different limits. Do you remember the type? What's the type? It's the jump. Always yes, thank you. Okay, I will skip the drawing. I will draw the last one because we need 4. 4 from the left, 4 from the right-hand side because it's 4 is after 3, and the value. Okay, ready. What's the limit at 4 from the left? Thank you. What's the limit of the function at 4 from the right? All the same thing. And what about the value? What is this? Who can tell me? Can you type the value for me? We did the value. Thank you, because it's so easy to say also -8, but no, the value is undefined. Because we remember that denominator. Okay, what type of discontinuity? Thank you, removable, because it's only 1 point removed. Limits actually are the same. Okay, and this is the graph I was drawing for you. We know that part, we know this one. This had 2 different limits. My scale is a little bit weird, but doesn't matter, the labels are correct. -7 was the limit on the left, and -8 was the limit at 4. Yeah, we can see how nice and easy we can, based on the limits. Okay, that's I think you know everything about continuity. Okay, let's keep moving, because we do have, I know I will not keep longer than 60 minutes, but thank you for your participation, it's excellent. Okay, now what I have on this slide, I think we know everything because we know the left and the right. This one probably it's obvious for you. If we would like to define continuity on the interval, we have to check every single point. Of course, we will not do, because if the function is continuous, like nice and smooth, we know that. But that's the definition. If function is continuous at every single number in the interval, then it's continuous on that interval. And we know left and right. Okay, this slide is telling me that if I have 2 continuous functions at A, I can add them, subtract, multiply by the constant, multiply by each other, divide, and I will still have a continuous function. That means the algebraic operations will still give me the continuous function. Also this one, if I will make a composition of 2 functions, 2 continuous functions, I also have continuous function. Okay, now, okay, this is important. Another property. It's so like nice and obvious, but we may be confused a little bit. That means what we have. some functions, like for example, polynomial, rational function, root function, trigonometric function, also like exponential, logarithmic, but this is more calculus too. But I list the important one. All of them, we can say that they are continuous wherever they are defined. That means I can say that they are continuous on their domain. Of course, polynomials are the easiest function, with the domain being all of the numbers. That's the reason that I type everywhere. Okay? That means polynomials, we have probably no problem, because polynomials are just the waves. Of course, they are nice and smooth, continuous. But what about the rational function? Right? Any rational function is continuous wherever it is defined. That is, it's continuous on its domain. The easiest rational function, it's 1 over x. Because rational function means the ratio of two polynomials, 1 over x. And do you know the graph of 1 over x? Probably you do. It's just the hyperbola in the first and the third quadrant. And what do you think? Is this really true that rational functions are continuous? Yeah, I mean, of course, I want to give you a few seconds to think. But what is, yes, thank you, Eric. That's actually the point. Yes, I was gonna try to trick you, but yeah, that's the thing. That we can see that 0, yeah, exactly, Alan, thank you. 0 is not, oh, my box is not nice. 0 is not in the domain. Yeah? And normally you will say, we will compute a limit and we will get negative infinity on the left, we will get positive infinity on the right, and we will call infinite discontinuity. But what this is telling us, that we're not looking at that 0 because it's not in the domain. That means wherever is defined means domain. And domain is, like Alan said, the first quadrant only, the positive axis and the negative axis. And we can see, I can draw this function without lifting the pen, nice and smooth curve, and then I can go on this side and the same thing. That means they are still continuous function. That means please look at this problem like that. And root function probably is okay, but trigonometric, we know, like, for example, tangent. Sine and cosine is fine, but tan of x, we do have like an asymptote, which we will call, yeah, that's tangent. And that's another part. Yeah, that's another part. And we can see, oh, we have this continuity, but we're not looking at the numbers where the vertical asymptotes are at. Okay? That's, we're just looking wherever the function is defined. Okay? That's important property. We will skip this. And I would like to solve this type of problem with you. That means let's solve it. And because I have one more theorem, and I'm thinking maybe I can. Okay, let's see. Let's do it, because I'm stressed about the time because we had fun doing the continuity. Okay, let's look at this, because that's more like the quiz type question. For what value of b is the given function continuous everywhere? That's what we see. Again, we see like a piecewise defined function. 1 is definitely a problem. And we can see on the left-hand side at 1, we have a quadratic function. This is continuous everywhere, no problem. At 1, it's exactly b. That means this will be a point. And 1 from the right-hand side is this function. The third degree polynomial, also continuous. That's what I have to make sure. I have to make sure that the limit of the function as x approaches 1 from the left is exactly the same, that the limit of the function as x approaches 1 from the right-hand side and is the same like the value. Okay? That means that's what I have to make sure. And now I can play with these equations and like try to match the a and the b value. Okay? And they asking for b. So let's see. limit 1 from the left-hand side. Do you know what formula shall I put here? Oh, hang on. Do you know what formula shall I? The first one, thank you, because I need your help, because you're actually really good. What formula shall I use from the right-hand side? The first one, thank you. 2ax plus 5. And actually, the value. Do you know what the value is? F exactly at 1? It's B. Oh, my B looks like 6. B. Okay, that's me. For now, I will just keep on this one, because then it's not helping me, the f of 1 and b. Okay, now who can tell me what is the limit on the left-hand side? It's just 1 plus a. Really good. We're just substituting 1. What's the limit on the right-hand side? What's the limit on the right-hand side? Actually, yes, 2 minus 2a plus 5. Okay. And do you think you can solve this equation for a? I can add. Yes, thank you. Okay, you have to help me. What's the value on the right-hand side? I add 2a to both sides. 2 plus 5 and minus 1. 6, yes. And what is a? A is simply 2. Okay, but now we have just a. Okay, a is 2. Do you think you know what's the value of b then? Or no? Okay, because you can see that's additional step. Plug 2 for e. Exactly. That means now if we have the value of a, what is the left-hand side limit? Left-hand side limit. Can you tell me what is this limit equal to? It's 3. Can you tell me what is the right-hand side limit? I believe must be 3. If this is 3, oh, 3, I say 2. 2 minus 4 plus 5. They have to be the same. That means if they are the same, then I can say the value at 1, which is b, must be the same. Okay, that means b is simply that value, 3. Well, we can see additional like step, but the main thing is the definition of continuity. Okay, and then what I have another question like that, but you can do exactly the same way. Okay, I will skip this question. And I think this is from your homework assignment. It's exactly the same idea. Okay, I will skip this one. Yes, yeah, it's exactly the same. You have to find the limit at 2 from the left and right, at 3 from the left and right, and just focus on these equations. Unless you would like me to solve this, we can solve it. And because what I have this for you, but I need like 10-15 minutes, and I can I can do this tomorrow. I can add this to the tomorrow's session. Oh, wow, I completely forgot that we decide to have 2 live sessions. Okay, let's try this one, okay? And this will be our last question. And you can help me. That means what we see 2 and 3 is the problem, right? That means I will write this. Limit as x goes to 2 from the left-hand side must be the same like the limit from the 2 from the right. Can you tell me what formula we will use on 2 from the left? First one, thank you, which actually I can even simplify. And can you tell me the 2 from the right-hand side? Who can tell me? Oh, I know you probably, but please give me like 4 minutes and we will be done. Okay. Okay, and now limit as x goes to 3 from the left Can you tell me what formula from the left at 3? The second one. Ax squared. Maybe you can give me the answers faster. And from the right-hand side, of course, is the last one. 4x minus a plus b. Okay. Okay, that means now, do you know what is this limit? Who can tell me that limit? Of course, it's 0 over 0. If it's 0 over 0, the answer for 99.9% is not 0. The answer is 4. Thank you. I will simplify. Oh, that's actually minus. I will get rid of the common factor, the common 0, and x plus 2, 2 plus 2 is 4. And can you tell me the limit on this side? Who can tell me? And I will type it. I mean, I will write it. 4a. We can just substitute 2. 2b, yes, thank you. 2b plus 1. 4a, 2b plus 1. I still can't do much. I can only make a little bit better and subtract. I can do this. And then I will have another equation, and I can solve a system of 2 equations. Okay, this one will be 9a minus 3b plus 1. Yes, thank you. Thank you, Maria. I didn't even realize. And what about this one? Who can help me this one? Just 4 times 3, yes. 12 minus a plus b. And if I will add a to both sides, I have 10a. If I will subtract b, 4b, and maybe 11. Okay. And what we can do, I can write this equation underneath. Okay, the first one we can see. And we have lots of different ways to solve a system of 2 equations. Okay. I can do by elimination, which means I will copy the first equation and I will multiply the second one, each term, by 2. 8a, 4b, and 6. By negative 2. Negative, positive, negative. I did multiply by negative 2, then I can eliminate b. Yeah, I can eliminate b. 10a minus 8a is 2a. 11 minus 6 is 5. Oh, I'm getting fraction. Hopefully I didn't make any mistake. You can check. That means a is 2.5. And if a is 2.5, I can substitute here and compute b. That means 2.5 times 4 is 10, minus 2b is 3. Then b is negative 7 divided by negative 2, which will be actually positive 3.5. That's positive. Okay, that's we have the value 2.5 and 3.5. And I hope I didn't make any arithmetic mistake. Yeah, if you will give me, is that 11 correct? Yes. Okay, but again, the idea, the main concept is this. Yeah, never make the mistake. And I can tell you on the quiz, and for this limit, do not put 0. Yeah, because that's what I saw, the main mistakes on the homework assignment, and especially on the quizzes. Yeah, do not put 0 for this one. It's actually 4. I can, because the rest of them is just algebra, which of course is also important, okay? But that's the calculus part. Okay, exactly 2 o'clock, and thank you very much. I really, really appreciate your attendance. And if you can attend the next session tomorrow, will be great. If not, of course, because I know that everybody has different schedule. Actually, I can switch the camera for 1 second at least. Okay, I'm still there. I was writing everything for you. And I hope you did enjoy the session. And as I said, I love the participation. Okay? Yeah. Thank you. Thank you very much. You can leave the classroom. Yes. Thank you, Eric. Thank you. Thank you, yes, Kendrick, Jake, Maria, I don't know, Regina. Yeah. Thank you. And please join me tomorrow. Okay? Tomorrow I will start this chapter 2, the derivatives. Thank you. Thank you very much. Thank you, Madeline. I don't know, Alan. I don't know if I want to say all of the names. Cody, thank you. Okay.